Had a lot of technical difficulties making this video, and this is about the point where it cuts out, so hopefully it works this time. So we need to go ahead and do our stoichiometry for this question. So I'm going to go to my notes. And I'm going to rewrite this for you. So we have C6H12O6, that's glucose. And then I'm not going to write out the full reaction because we don't really need it. And then we had 2803 kilojoules. So this is the stuff that we need from that question. So first we're going to write what we know above. In the question it said that we had 21 grams of glucose. We're looking for energy, so I'm going to put my X over here. And then you can just bring, oh my goodness, you can just bring this number down. In the question, it told you that it was negative, so I'd go ahead and put that negative sign right there. And on this side under glucose, we have to have the molar mass. Because we have grams on the top, we have to have grams on the bottom. So go ahead and calculate the molar mass real fast, and I will do the same. And then you can check your answer. So I got 180.156. So now I'm just going to cross multiply and divide. I can do 21 times negative 2803. I'm going to divide all of that by 180.156. So when you do that, you should get your answer for the problem. Now I got negative 327 kilojoules. So that negative sign is telling us that it is exothermic. You could also have just left it positive and said that it was released. So 327 kilojoules released and negative 327 is the exact same thing. Next, we're going to talk about measuring enthalpy when it's not given in the question. There's 4 different ways to calculate the enthalpy change, which is delta H, of a chemical reaction. The first one is using calorimetry, using the calorimeter to experimentally measure the heat released or absorbed during a reaction. We're going to talk about that in a little bit. Number 2 is Hess's law, using other chemical reactions to solve for the heat of the reaction, which we will practice next class. Number 3 is heat of formation, using a table of potential energies, measuring the potential energies of the reactants and the products to calculate enthalpy change. So we could use this equation. The change in enthalpy is equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. So that weird symbol that looks like an M sideways, that means the sum of. The last one is you can add the energy it takes to break the reactant's bonds and subtract the energy released when new bonds are made. So it would look like the energy from the bonds broken minus the energy from the bonds made. So we're going to talk a little bit more about calorimetry. Here is a calorimeter off on the right side on that picture. Usually it's going to be some styrofoam cups. This is something we could build easily in class, which we will do next week during our lab. It's used to measure heat. It's an insulated device that's going to capture all of the heat, either absorbed or released by a chemical reaction. The reaction is usually surrounded by water because water is stable and it has a high specific heat. Excuse me. Having a high specific heat means that the water temperature changes very slowly so that we can actually measure it. The heat of the reaction is going to be minus whatever the heat absorbed by the water is. By measuring the heat that the water absorbs and releases, we can calculate the heat of that specific reaction. Remember that heat is going to be symbolized by lowercase q, and it's the transfer of thermal energy between two objects that are at different temperatures. Temperature is an indirect measurement of the thermal or the heat energy. And remember that temperature is not the same thing as thermal energy or as heat. We can calculate heat. That's going to be represented by lowercase q. Again, that's what is absorbed or released by the substance, and it's always going to be this equation, Q equals mc delta T. So Q is heat, M is mass of the substance. Sometimes that might be the mass of the water if we're using a calorimeter. C is specific heat. For this class, I will always give you the specific heat. And delta T is change in temperature. That is the final temperature minus the initial temperature. So here's some specific heats that we know of. Notice H2O at the bottom is 4.184. That is an important number. The specific heat, capital C, of a substance is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. It tells us indirectly how well a substance can absorb or how well it can hold heat. A high specific heat means that the substance can absorb or release heat very well without changing temperature a lot. So if there is a temperature change, it's going to happen slower so that we can actually measure it. A low specific heat indicates that a substance cannot absorb or release heat very well, and it's going to change temperatures really quickly, and it's going to be very hard to measure that temperature change. So let's work on an example. This says, how much heat is given off when 869 grams of iron bar cools from 940 to 50 degrees Celsius? So we're going to use this equation. I know that my specific heat of iron is 0.444. That will be given to you on a test. Mass is what's given in the question, and our change in temperature is our final temperature, 50, minus the initial temperature, which is 940, so I would get negative 890. When I multiply all of those things together, I would get my answer. So Q is negative 34,000 joules. That's how much heat energy would be given off. Here's another example. It says a 0.1964 gram sample of solid C6H4O2 is burned in a bomb calorimeter, that's just a type of calorimeter, that contains 373 grams of water. The temperature increases by 3.2 degrees. Calculate the heat lost. Okay, so here's my equation. Here's my thing that I'm going to use to solve for Q. So I just can fill in what I already know. In this case, I'm using a calorimeter, so my heat of the reaction is just the negative of whatever I'm about to calculate. I just need to add a negative sign on it. So my mass is the mass of the water, since we're using a calorimeter, which is 373. Then I have my specific heat of water, which is 4.184. And then I have my temperature change, which is 3.2. When I multiply all of those together, I get 4,994.02 joules. That's the heat energy of the calorimeter. Just a second.
Pardon this interruption. Jalen Reyes, please come to the office. Jalen Reyes, please come to the office.
Okay. Sorry about that. All the bells today. So this is the heat energy gained by the calorimeter. For the actual answer, it's just the negative of that. So my negative is negative 4,994.02 joules, and that's my answer. So you have an assignment in your slides to work on. You can use your notes for that. And then do not forget to do the exit ticket in Google Classroom and complete any missing work you have.